So in this video, we just want to justify the claim that the second mixed partial derivatives are in fact equal. So the claim is that if we compute f of xy and f sub yx, that we'll get the same result every time. So the justification for it would be just to calculate initially the first partial derivative with respect to x. And to do that, we have to apply the definition of a partial derivative. And the partial derivative definition says apply the difference quotient, take the limit as h goes to 0, on the difference quotient of being applied to the x variable. So when we do that, it looks like this. We get f of, we do our x plus h, we vary x, and then y, minus, and then we do f of xy, and it's all over h. And to get the derivative, we take the limit of this difference quotient as h goes to 0. So if we were going to calculate the mixed partial f sub xy, where you take the derivative with respect to x and then take the derivative of this result with respect to y, we would need to take partial y of our derivative taken with respect to x. But that would mean just apply the difference quotient to this function right here by varying y and holding whatever you see in the x position constant. So if we do that without erasing our x from the previous line, so what we would do, we're going to get this varied with respect to y minus the function all over h. So we're going to get a ratio all over h. So it's going to be f of, and I'll put the limit first. We need to take the limit as h goes to 0 to get the second partial derivative. Apply the definition of a derivative. So if I'm taking it with respect to y, I hold the stuff that's already in the x position constant, so the x plus h stays, plus now we're going to vary the y, so we're going to get y plus h, and our function is minus f of, hold the x constant, vary the y, so we get y plus h. And then this function's all over h, so I'm going to put it all over h, and then it's a difference quotient, so it's minus the function itself, and the function itself is just f of x plus h comma y minus f of xy all over h, and then we're doing the difference quotient, so we take this difference all over h, and we're taking this difference as h goes to 0, right? We're taking the difference as h goes to 0. So now I have the second we have a mixed partial where we do take the derivative with respect to x first and then take the derivative with respect to y second. So this guy right here is just f sub xy. If I go down to the bottom of the screen and say, hey, what would I do if I were calculating the first partial derivative with respect to y? Well, I would take the limit as h goes to 0, and I would do the difference quotient, but I would be doing the varying on the y and holding x constant. So I would get f of x comma y plus h minus f of xy. There's the difference quotient applied to variable y, and it would be all over h. And to get f sub yx, the mixed partial where I take the derivative with respect to y first, then x, I would take partial x of my f sub y. But if I'm taking the partial with respect to x, that says hold the y is constant, and then everywhere you see an x, first replace it with an x plus h, and then subtract the original function and put it all over h and take the limit as h goes to 0. So we would want to take the limit as h goes to 0. Now everywhere I see an x, there's one, I'm going to replace that x with x plus h. I'm going to hold whatever's in the y position constant, minus, my function has a minus, my function has f of x y, but everywhere I see an x, I replace it with x plus h, and I hold the y term constant, and my function is all over h, and now I have to, it's a difference quotient, so now there's the difference part, subtract the original, So the original is just f of x comma y plus h minus f of xy all over h. And because it's the difference quotient, I take the difference and I put the entire difference over h, and I take the limit as h goes to 0. So if I look at, and so this guy right here, he's f of, we did the derivative with respect to y followed by the derivative with respect to x. So I have f sub xy and f sub yx right here. And what we want to notice is that we have a subtraction going on in the numerator of each of these. And the denominators are the same for each of the numerator terms. And if we look at it, if we because the denominators are the same, we could switch the order of the subtraction right here. I could move this guy over here, and I could move this guy f of x y plus h over into this position, because I just have minus minus, and we could switch the minuses. If I switch them, though, I'm going to have exactly what I have on this line. So they really are, these two statements are equivalent. What you wind up with when you do them is, you get a common denominator where everything's over h. So I could write it like this, and I have the minus e here, and the order of these minuses isn't going to matter. I can switch the subtractions, and if I switch the subtractions right here, then I get, would just be over a single h. I lost my big fraction bar. My numerator would look like this, and I would have exactly the same thing I have for this mixed partial. So mixed partials are equal. Of course, there's certain things you have to pay attention to. Are your mixed partials continuous on an open set containing the point you're interested in? So there's some things we need to pay attention to, but mechanically it works out that the calculation for the two mixed partials is equivalent.